Thank you again, and welcome to Beckman Coulter webinar series. My name is Chad Schwartz. I'm an application scientist in the centrifugation division at Beckman Coulter here in Indianapolis. Today we are excited to introduce Dr. Osman Bakr, who is an assistant professor of materials science and engineering at King Abdullah University of Science and Technology. Dr. Bakr received a Bachelor's of Science from MIT in 2003 and went on and received a Master's of Science and PhD in Applied Physics from Harvard University in 2009. Today our webinar will cover the physical and chemical characterization of nanoparticle constructs using the Beckman Coulter Analytical Ultracentrifuge. So without further ado, I would like to hand over the slides and control to Dr. Osman Bakr. Thank you.
Thanks, Chad, for the introduction. Thank you all for coming over here today to attend the webinar. My name is Osman Bakr, and I'm here to tell you about how to characterize nanoparticle constructs using the Analytical Ultracentrifuge. My talk is divided into 3 parts. In the first part, I'm going to be telling you about the challenges of analyzing nanoparticles, particularly because they have heterogeneous partial specific volumes, and how to solve that problem. And then I'm going to be telling you about a general method that was recently developed using a software package to directly fit nanoparticle size distributions. This method is called the custom grid method that was developed by Boris Demler. And then finally, I'm going to conclude my talk by discussing some experimental considerations one should think about in order to avoid artifacts in measuring nanoparticles. I'd like to thank Beckman Coulter's Analytical Ultracentrifugation team for inviting me to this webinar, and I'd like to also thank Boris Demler for providing some of the slides for the custom grid method. Before going further, I would like to conduct a poll to figure out the background of the audience. So the first poll, and please do take a minute to participate, asks about if you're familiarity with the Analytical Ultracentrifuge. So kindly just answer the question so we could get an idea about the background of the users. Okay. So I guess we got the response from most people, and it looks like about 2/3 of you are novices, and maybe about 10% are very experienced users, and about 20% are somewhat familiar with the Analytical Ultracentrifuge. My second question is, what is your experience with nanoparticles? Have you used them before in your research, and do you plan to use them in your research? Okay. Okay, so it looks like most of you are familiar with nanoparticles. And finally, I'd just like to ask the following question. What method do you use typically what is the primary method that you use to analyze your nanoparticles? So we have electron microscopy, analytical ultracentrifugation, dynamic light scattering, field flow fractionation, gel electrophoresis, and we have mass spectroscopy, or if none of the above. So it looks like most of you use electron microscopy and dynamic light scattering, and some of you have been using analytical ultracentrifugation and other methods. In general, it seems to me that many of you are new to analytical ultracentrifugation, particularly to nanoparticles. So I'm going to start off slow and try to take the topic from the beginning. All right. So just before I start, I'd like to introduce some useful references on the topic. So these 4 papers are very useful for anyone interested in studying nanoparticles with the analytical ultracentrifuge. The first paper is by Stelacci and myself, and it covers the how to use analytical ultracentrifugation to solve for the partial specific volume of nanoparticles. The second paper is just published recently in Analytical Chemistry by Boris Demler, and it covers a general method and a software package that one can use to analyze the distributions directly of nanoparticles. And then I'd also recommend a recent paper in ACS Nano by Pukert and Wolleben and Colfin, where they highlight some new methodologies to study nanoparticles, especially in terms of instrumentation. And then I'd also recommend a very good review published in 2010 by Plankin and Colfin that covers nanoparticles and generally gives an idea to beginners of what are the challenges when studying nanoparticles. Okay, so first off, I'm going to discuss about the challenges in studying nanoparticles and how to solve them. So for those of you who are not familiar with nanoparticles are typically a composite material, typically containing a core that's inorganic and a shell that's organic. Usually we have to use multiple modalities of methods to analyze the different parts of the nanoparticle. So for example, the overall particle diameters typically people use dynamic light scattering or field flow fractionation, maybe gel electrophoresis, while for the particle core, people would use electron microscopy or mass spectroscopy. And then one has to combine many methods in a global analysis to figure out what's going on with the nanoparticle. But that's actually quite difficult to do, because nanoparticles not only have a diameter variation, but they also have a density variation, because as the particle size changes, also does the ratio between the organic component in the shell and the inorganic component in the core. Okay? So what that means is that you have a heterogeneous size distribution that's very difficult to analyze with a global method, and so we need a single method that can analyze both size and density variation at the same time. So the question is, how can we measure size, mass, and density distributions in nanoparticles? Now since most of you have used electron microscopy and light scattering to study nanoparticles, I'm going to just highlight some of the shortcomings of these methods. First off, if you're going to use electron microscopy, nanoparticles typically have an inorganic core and an organic shell. Electron microscopy it's very difficult to image the organic shell with the electron microscopy because of the low mass of the organics. So typically electron microscopy is only useful for the study of the core. And moreover, because of particle size counting, typically your sample size is tends to a few hundreds of particles, and because you're looking at the projection of the particle in a two-dimensional plane, you end up with a significant sizing error, and perhaps a misrepresentation of your particle. So for example, here we have a atomically monodispersed particle, but because it's on the electron microscopy grid in different orientations, it seems as if this particle has a size distribution when in fact it's one single species. Finally, if you're using light scattering, you can imagine that the biggest particles in your size distribution typically dominate, but also for size distributions that are less than 10 nanometers, it's almost impossible to get any mass information. Okay. Analytical ultracentrifugation seems like a very ideal method to study nanoparticles. For those of you who don't know what an analytical ultracentrifuge is, in the simplest terms, imagine you have a distribution. You have a two-component system of nanoparticles, or an arbitrary number of components in solution. And so, if you subject them to a gravitational force field, then they're going to sediment at different rates. And if you can monitor the sedimentation process with somehow optically or any other way, then you could actually follow the sedimentation and diffusion of these particles and measure them. And so what is nice about this process is that you could actually do it in solution and also count over millions and millions of particles. And so you have a statistically robust idea of what your nanoparticle distributions look like. Now, many of you have used the analytical ultracentrifuge to study proteins. However, actually, historically, the analytical ultracentrifuge was developed by Svedberg to study nanoparticles. And what Svedberg said is the following: if you know the viscosity, or if you know the viscosity and the density of your solution, then you can figure out the diameter of your species and its molecular weight if and only if you know the density of the species of the particle. So we can measure the sedimentation and diffusion coefficient with the analytical ultracentrifuge, and if we know the density, then we can figure out with the Svedberg formulas what is the molecular mass of the particle and what is its diameter. Okay, but the problem is with nanoparticles, we don't know what the density is, and there's a density distribution. So what we need is a method where we could just measure the sedimentation and diffusion coefficients and then obtain the density distribution and mass and diameter all from the analytical ultracentrifuge. Okay, so for those of you who are not familiar with the analytical ultracentrifuge, typically inside the analytical ultracentrifuge you'll find there's a rotor, and normally you would load your sample, and there would be a sector where you load your sample, and a sector where you load your reference solvent. And as the rotor is rotating, you have an optical detector that scans the sample and reference sector and creates profiles. These profiles are recorded over time, and these time recordings are analyzed then to obtain the size distributions. There are many kinds of detectors that one can use. There's absorbance, there's interference, and there's also fluorescence. Since many of you are new to this, I just like to tell you a bit about how nanoparticles sediment in a gravitational field, or how just particles in general. So a particle subjected to a gravitational field will sediment and will feel three kinds of forces. The first force is the centrifugation, which is omega squared r times the mass of the particle. But there are also two other forces. One is the buoyancy force, which is related to the ratio of the particle's density to the solvent's density. But also there's an opposing force that is the frictional force, which is proportional to the frictional coefficient of the particle times its velocity. And so typically the particle reaches terminal velocity within microseconds, and all these forces balance out. And then if you sum up all the forces, you could obtain an expression that relates molecular weight, frictional ratio, and particle density to a quantity called sedimentation, defined as a sedimentation coefficient, which is essentially the particle's velocity divided by the gravitational force, or the centrifugal force. Now, if you use the Stokes-Einstein relation, you could rewrite the frictional coefficient in terms of the diffusion coefficient, and so you obtain one of the well-known Svedberg formulas, where the molecular weight is equal to sedimentation coefficient divided by the diffusion coefficient times the gas constant times temperature, related to the density of the solvent divided by the density of the particle. Now, if your particle is a sphere, an ideal sphere, you could use Stokes' law, where you could write the diffusion coefficient in terms of the diameter of the particle and the viscosity of the solution, and you would get also the well-known Svedberg formula, which relates the diameter of the particle to the viscosity of the solution and the density of the particle and sedimentation constant. Now, if this is true, then you could also rewrite this expression to obtain an expression for the density of the particle in terms of the diffusion coefficient and sedimentation coefficient, and the viscosity of the solvent and the viscosity of and the density of the solvent. So this is only true if we know what the shape of the particle is, and if it's a sphere, if it's a perfect sphere. Now, the question we asked is, we know that nanoparticles are not perfect spheres, and they typically look like this, but how good of an approximation is it if we assume that they're Stokes spheres? Okay. Usually when nanoparticles sediment, there's more than just sedimentation force acting on the nanoparticle, because one creates a diffusion gradient, a concentration gradient. So there has to be a diffusion flux created by the sedimentation, and the sum of the diffusion force and the sedimentation of the particle leads to an equation called the Lamb equation, which describes exactly how a particle evolves, or how the particle sediments and moves inside a centrifuge when diffusion and when subjected to the gravitational force. Okay, so the term on the left is a diffusive term, and the term on the right is a sedimentation term. There's two types of there's two kinds of major experiments that one can do with the analytical ultracentrifuge. One of them is called sedimentation velocity, which is the mostly used method for nanoparticles, and in this limit, the sedimentation is much larger than the diffusion, and so the particles end up moving all the way through your sector, and you could monitor them over time. Now, the other method, which is used a lot in proteins but much less with nanoparticles, is called sedimentation equilibrium, and in this case you have you use a very low sedimentation, a low gravitational force, basically a low rotational speed in your centrifuge, and in that case the diffusion is comparable to the sedimentation, and you get a diffusion profile where at equilibrium can tell you something about the molecular weight of your sample. But this method is very difficult to apply with nanoparticles, because nanoparticles have a very heterogeneous size distribution. So we're only going to deal with right now with sedimentation velocity, and for most people, sedimentation velocity is the way to deal with nanoparticles. The Lamb equation that's used to describe nanoparticle sizes, the evolution of nanoparticles or anything inside the centrifuge, is very difficult to solve analytically, and it's typically solved through finite element methods. and there are good software packages to solve them. One is called SedFit, and the other is called Ultrascan. So you could use these after you do your experiment inside the centrifuge. You collect your data. You can take that data and fit it using these either one of these software packages, and they would give you your distribution of sedimentation coefficients and diffusion coefficients. Okay, and here's an example of a sedimentation and diffusion map, and each one of these hotspots in these maps represents a species in your sample. Okay, so you could obtain the sedimentation and diffusion coefficients, and now we go back to the question of solving nanoparticle molecular weight and density and size and density distributions. So if we assume the particles can be treated like a sphere, then we could actually write an expression for the density, and if we know the sedimentation and diffusion coefficients, then we could obtain the density distribution, molecular weight distribution, and diameter distributions. Okay, so this is a hypothesis, and so we have to prove this hypothesis. And in order to prove this hypothesis, we have to use some model systems. Now, the best model systems I found is a class of nanoparticles called atomically monodisperse metal clusters. And there's a lot of reports in gold and silver. And what separates these nanoparticles from normal nanoparticle systems is that these have a precise molecular weight and a precise structure. And so they actually can be measured by X-ray crystallography, and they can be measured by mass spectroscopy. So everything about them is very well defined. And what we did is that we took three sizes of well-known particles. One is gold 25, and the other is gold 38, and the other is gold 144. Their sizes were determined by mass spectroscopy or X-ray diffraction, and so they're very well defined. And we put them in solution, and we tried measuring them in the analytical ultracentrifuge. And so we did this, and we could what's really nice is that you could separate them out, and you could detect their diffusion coefficient and their sedimentation coefficient and their diffusion sedimentation coefficients. And so, as you can see, all these three hotspots correspond to each particle. Now, because of that, if we use the formulas we've I've shown you in the previous slides, then we could transform the sedimentation and diffusion coefficients into a diameter and a density and a molecular weight. Now, if our formulas are right, then we'll get the molecular weight, an accurate value for the molecular weight. And what we find is that if we compare the molecular weight measured by AUC with the molecular weight measured by mass spectroscopy or X-ray diffraction, then we get an error of less than 5%, which is quite good. So even though those particles are clearly not Stokes spheres, we could use the Stokes spheres approximation to analyze these particles that have a low aspect ratio. And what you notice is here is that this is something that you can't do with dynamic light scattering. If you look at the diameter of the particles we've measured, they only differ by fractions of a nanometer, by a few angstroms. So the smallest one is 2.4 nanometers. The biggest one is 2.8. And so what's really really advantageous about the analytical ultracentrifuge that you would not be able to see in any other method is that these small differences in atomic number would manifest themselves in sedimentation and diffusion coefficients. And you could do something more once you've measured the density and the molecular weight of the particle using the analytical ultracentrifuge. You could actually look at the different components of the particles, and if you know the density of the different components, so for example, if we know that the core is made of gold, and we know what the density of gold is, and we know that the shell is made of some organic material, and we know what its density is, then we could actually figure out what the composition of the particle is. So, and here we can compare the composition obtained just from the densities of the particle with the actual composition obtained from mass spectroscopy, and we see, we're not too bad off. We're only a few atoms off, and I'm not saying you could use this method to precisely determine the composition, but you could use it actually to tell you which compositions are the ballpark compositions you should be looking for. And that's especially useful for people who are using mass spectroscopy, because in mass spectroscopy there often is a lot of fragments, and it's very difficult to analyze a mass spectrum if you don't know what roughly the size of your particle is. Now conversely, if you know what the molecular formula of your nanoparticle is from the mass spectroscopy, then you could actually use that information to obtain a density, the density of your of organic material in your ligand shell. Okay. So depending on how much information you have, there's a lot of different things you could obtain from just analyzing the density of your particle and its total molecular weight with the analytical ultracentrifuge. Now I want to also go beyond atomically monodisperse clusters, and I want to show you some things that you would not be able to see with conventional methods like electron microscopy. So for example, here's what seems to be a very monodisperse size distribution of nanoparticles, and they form superlattices. And if you measure their size distribution with the electron microscope, you'll see that they're about 6.7 nanometers with a less than 5% size distribution. However, when you analyze them with the analytical ultracentrifuge, you realize that there actually is not one species, but in fact there's actually two species. And both species are very close in size in terms of core. So one is 6.8 nanometers and the other is 6.7. However, what really differs between the two species is one of them has much more organic material than the other. So this is something you could not have seen with the electron microscope alone. And also, if you do particle sizing with the electron microscope, what you see normally is a broad size distribution. So you have many kinds of nanoparticles, and you're seeing their different projections. And however, if you study them with the analytical ultracentrifuge, you notice that actually what was a broad size distribution is actually comprised of individual discrete peaks in your sample. And so that tells you that your sample is not a broad distribution, but in fact is composed of individual species. And what you could do actually, if you do your experiment correctly, you could even measure diameter and the density of each species in solution. Okay. Now I wouldn't normally, if you have too many species in solution, I would not recommend doing this kind of analysis with the analytical ultracentrifuge. I would recommend first trying to separate your species into more monodisperse fractions, for example by density gradient centrifugation, or by improving your synthesis. Now, okay, so now I'm going to go into the, now that I've described to you how to solve the problem of the partial specific volume, I'm going to go into a general method that was developed recently by Boris Demler to map out the distributions of nanoparticles directly using one of his software packages, which is called Ultrascan 3. So this is the paper, the reference for this method, and a lot of the information in the slides I'm going to present to you are summarized, are taken from this paper. So if any of you have used a software package to analyze proteins or nanoparticles, you'll notice that in the analytical ultracentrifuge, the software package requires you to input the partial specific volume of your nanoparticle or your protein. Now this is okay for a protein, but because proteins can have a constant partial specific volume, and what the software package does it fits the diffusion coefficient and sedimentation coefficient in terms of the frictional ratio and the molecular of your nanoparticle or your protein. So you get a distribution where you have a sedimentation coefficient in terms of the frictional ratio, or you get a molecular weight in terms of the frictional ratio. However, as we remember with nanoparticles, you can't do that because we don't know what the partial specific volume is. So what Boris did is that he developed a method called the custom grid method, where we can choose which parameter to fit to the sedimentation and diffusion coefficient. So for example, if you know how to measure the partial specific volume, as in proteins and polymers, through densitometry, then you can fit the frictional ratio. But if you know or in the case of nanoparticles, you know what the particle shape is, then you can in fact input the particle shape and have the program fit the partial specific volume or the particle density. Or in some special cases, if you know what the molecular weight of your particle is, through mass spectroscopy, then you can fix the molecular weight and fit the particle shape and particle specific volume. In the case where you need to where the molecular weight is known, then through mass spectroscopy you input the molecular weight and the program gives you the partial specific volume and the shape of the particle. And this is a module in Ultrascan 3. Okay, here's an example of a particle where that was measured in the Analytical Ultracentrifuge, and the particle has a well-known molecular weight. And if we fix the molecular weight, we could obtain the particle information about the particle's frictional ratio, which is essentially its shape, and information about its density or partial specific volume. Okay, and on the other hand, this is the more general case where we typically can use electron microscopy to figure out what the particle shape is or particle anisotropy is, and so we can fix the particle shape and fit the diffusion coefficient to the molecular weight and particle density. And here, one example is I'm about to show you is the case where we deal with quantum dots. Okay, in quantum dots have a core that's luminescent, and that luminescence is related to the particle size, and so it's very easy to figure out what the core size is from the luminescence or the absorption wavelength. But you need to know, for example, what is the density of the organic material in the shell. So for example, for people working in the biomedical field, conjugate organic molecules or drugs to the nanoparticle, and they want to figure out what the density of the organic material that's conjugated to the nanoparticle. And so essentially we know that the shape of the particle is roughly spherical. So what we do is we analyze the particle as if it has a fixed shape, and we can approximate the shape as a sphere. So it would have a shape factor of equal to 1, and then when you do this analysis, you obtain a distribution of sedimentation coefficients versus the partial specific volume, and hence you could transform this distribution and create a table where you obtain the different masses and densities of each species of quantum dots, and then from there you could obtain the density of the organic component in the ligand shell, because we know what the core size is from the absorption spectrum. Okay, so finally I'd like to just describe some important experimental considerations one should take into account when analyzing nanoparticles, so to avoid artifacts. And the first thing one should be careful of is to choose a proper buffer to dissolve their nanoparticles. Nanoparticles need to be colloidally stable in order to get a proper measurement in the analytical ultracentrifuge. If you choose a buffer condition where the nanoparticles are not very stable, then you end up measuring not just the nanoparticle itself, you end up measuring its aggregates, and so the measurement becomes very ambiguous, and it's not clear whether the aggregates represent an individual species or the aggregates represent an individual particle. So here we have a particle, for example, that's in its most ideal buffer is actually an individual species. However, if you choose the wrong buffer where these nanoparticles are not that stable, then they can aggregate, and you would see that aggregation. However, in this case, we know that the nanoparticle is monodisperse, so we know that the aggregation is an artifact of the wrong selection of a buffer. But in many cases, we don't have this the luxury, so we have to try different buffers to make sure that the samples are colloidally stable. So you would have to measure your sample in different buffer conditions, just to check if the size distribution changes or not. The second consideration is that concentration. So typically, you would like to select a concentration range where your nanoparticles don't interact a lot. Okay, so if you choose for example, a nanoparticle concentration. Same nanoparticles measured at 3 different concentrations, and if you choose a concentration range where the nanoparticles interact a lot, then you will get a non-ideal sedimentation, and you'll also get a size distribution or sedimentation coefficient distribution that's not representative of your nanoparticle. So ideally, when you measure your nanoparticles, try to measure them at 3 different concentrations: at a high concentration, a middle concentration, and a very low concentration. The final consideration this is something that one hardly observes in proteins, but it's very common with nanoparticles. Now the sectors where you load the nanoparticles in are can be made of typically three kinds of materials: either a charcoal EPON material, which is kind of a polymer, or aluminum or titanium. Now, ideally, you would like to use the charcoal polymer because it interacts the least with nanoparticles. However, you have to keep in mind that, most nanoparticle systems are not just run in water; they're run in organic solvents, which can destroy the centerpiece. So then you're left with trying either the aluminum centerpiece or the titanium centerpiece, and often you have to check first whether your nanoparticles react to the centerpiece or not. So you could see on the left-hand side a comparison of the same nanoparticle run in a titanium or an aluminum centerpiece, and you would see that, for example, the nanoparticle reacts with the aluminum centerpiece more than the titanium. That's not a general case, but you would have to try the different centerpieces to check whether your nanoparticles are stable. So what I would do is I would put the nanoparticle solution inside the centerpiece, and I would check its absorbance over time, whether the nanoparticle stays stable or not. If the absorbance changes over time, then that's a good sign. That's a good sign that it's not stable, and you have to find either conditions where the nanoparticles are stable or a centerpiece that stabilizes, that doesn't react with your nanoparticles. So typically, you have to remember with metal nanoparticles, things like aluminum can galvanically exchange with the nanoparticle. So, all right. In summary, I'd like to summarize this talk by saying the main points is that you could measure simultaneously size, density, and molecular weight distributions of nanoparticles using the analytical centrifuge if you know what the frictional ratio is, and through some method, other method like electron microscopy or X-ray diffraction. you could distinguish between particles that differ in diameter by a few angstroms using the analytical ultracentrifuge. That's one advantage you would not find with any other method. And what's really beautiful about it is that you could do this in solution in the native state of your nanoparticle. And then I'd like to say that a lot of times, to our surprise, you could estimate many nanoparticles as Stokes spheres, especially if they have very small aspect ratios. And then finally, I'd like to say that you could obtain information about the organic component in the nanoparticle if you know something about the core through other methods such as electron microscopy, or beforehand you know what the density of the core is. I'd like to conclude this talk by thanking my collaborators, Boris Demler and his group, Gary Gorbett, Virgil Scherf at the University of Texas Health Science Center in San Antonio, and Randy Carney and Francesco Stellacci at EPFL, and Tiklam Nagoyan and Paul Mulvaney at the University of Melbourne. Thank you for listening to me, and I'm open for questions.
Thank you, Dr. Bakr. It was a very, very informative talk, and you are clearly a pioneer in the field. We've received very good questions from our audience, especially a couple questions about aggregation. So Victoria Virador asked, how do you deal with nanoparticles that have a high tendency to aggregate in solution?
Okay, that's a very good question. So my first answer is that you need to find a buffer where they or a solvent that minimizes the aggregation as much as possible. And the second thing you need to do is basically you have to use a preparative centrifuge to get rid of the aggregates before you run your sample. And the third thing I would do is also run the sample at the lowest possible concentration that you can, and this is how you would minimize aggregation as much as possible. It is a big problem, but it's something. But this is how you would mitigate it.
Great.
Yes.
Thank you. Those are some great suggestions. Alexandra LaCroix asked, if you functionalize the particle with a biomolecule or drug, how well can you characterize your system? Could you determine the ligand density and distribution of your particles relative to the naked nanoparticle?
Yes, you can. What you need to know, you need to know, first of all, you need to know what your particle is, what your particle looks like before you've conjugated it. So you need to measure your particle in the centrifuge before conjugation, and then you would measure it after conjugation. And it would be also good if you can figure out approximately what the core, something about the core diameter through a method like electron microscopy, because then you could combine that information and you could obtain very quantitative data about measuring the ligand density. There is actually a paper, I guess in 2009 or 2008, that was by Mulvaney's group, where they actually do try to address that question, and you will also address this question in both the paper we have in Nature Communications and the paper that was published by in Analytical Chemistry by Boris Demler. So yes, you can actually use this method as long as your as long as what you use to conjugate is does not significantly change the overall shape of your particle. So if you have a particle that's a few nanometers and you conjugate to something that's 100 nanometers, then I wouldn't advise to do that. But if you have a particle that's if your conjugate is on the order or comparable in size to your particle, then this is a very useful method to do. Yes.
Great, thanks. And we are continuing to receive questions, and we will try to get to as many as we can. A question from Asad Karim out of the University of Karachi was wondering whether or not you can use AUC for liposome nanoparticles. That's a good question. I have not tried it in person, but I think in principle it should be possible. It should be as long as you could detect the liposomes with one of the optical detectors on the Analytical Ultracentrifuge. It should be okay. And the other thing is, the liposomes should be relatively stable, so they shouldn't be dynamically changing during the experiment. I mean, you could get some interesting information in the Analytical Ultracentrifuge by monitoring this dynamic change, but you cannot get information about the size distribution of the liposomes if they're changing during the experiment. Okay. Yes. Second question. Okay.
Next question.
Another follow-up question, I guess. We're getting a lot of questions on different types of nanoparticles. If you could just comment, I know we've already talked about liposomes, but it seems people are asking questions about other biological nanoparticles as well as, say, nanorods. Could you just make a general comment on how AUC is able to characterize all these different things?
That's a good question. So things like nanorods and you need to in order to get, you can always get very good actually qualitative data from the Analytical Ultracentrifuge, even if you don't know anything about the density or the particle shape. However, for things like rods, you need to estimate what the particle shape is and estimate what the particle even for any other molecule that has that have very large aspect ratios. You need to figure out what is the frictional ratio for that specific specific shape. And there are actually programs developed by the centrifugation community, and there are actually also analytical formulas that can give you the frictional ratio for a given shape. And so once you know what the shape is, you could use the custom grid method in Ultrascan 3, and you could input the particle shape, and it would fit the program would fit the particle density or partial specific volume and molecular weight based on the shape you've given. I would say the only thing that would constrain this method is that if you have also a distribution in particle shapes. So then your problem becomes very difficult to analyze. You have to either have a fixed particle shape or a fixed density. If you have either one, then the system can be analyzed quantitatively. But if you have both a heterogeneous size and heterogeneous density and a heterogeneous shape, then you will not be able to get quantitative data from the Analytical Ultracentrifuge. Next question.
Okay. Thank you. Another question, and it brings up a good point, from Anatoly Andreyko, asked, if you calibrate the system, does AUC require any type of standards?
Good question. So this is one of the AUC's strongest point. AUC is a first principle method. It does not require any calibration at all. No calibration, nothing. It's the theory behind AUC. All the equations are derived from first principle thermodynamic equations, and so all you need to do in the AUC is make sure you're measuring your sample at a fixed temperature, and you know the viscosity and density of your solvents, and all these are actually very easy and straightforward to do. So you don't need any unlike any other method, most other methods like chromatography or gel electrophoresis, or the AUC does not require any standard. It's an absolute method.
Great, thank you.
Yes.
And a very good point there. A follow-up on that by Robert Wetton from the University of Texas. He brought up the point that there are other methods such as chromatography and electrophoretic mobility for particle size analysis. How would you compare the results as far as accuracy obtained by these methods compared to AUC?
Okay, that's a very good question. And in terms of separation, the ability to separate different species, I think electrophoresis and AUC are comparable in terms of being able to separate species. However, and chromatography is also reasonably okay. However, AUC is a much more general method because unlike, for example, chromatography or AUC, you don't need any specific interaction. So, for example, in electrophoresis, you need the particles to be charged, and typically you need an aqueous solvent in order to run your sample. For chromatography, you need some sort of interaction between your stationary phase and the particle, and this is not something. It's not something trivial to do. While in AUC, the particle, all you need is your particles to be stable in solution, and the solvent can be almost anything, any solvent, or the organic or solvent or aqueous solutions. And the separation is related only to mass and density, and so it's a more, in my opinion, it's a they all offer different, especially electrophoresis offers information on the charge, but as a separation method, AUC is much more general separation method. But also with electrophoresis, you need standards, while in AUC you don't need a standard to measure the size of your material. And with chromatography, you typically need a standard as well.
Okay, thank you. We'll get to one more question before the end of the hour. Nikolay Kolosov asked the size range of nanoparticles using AUC.
Okay. That's a good question. So AUC, in theory, AUC works on nanoparticles of all sizes. However, a big particles that are very big, they sediment very quickly, and they require very low rotational speeds. The actual instrument is limited to about 3,000 RPMs, and so that means that particles that are typically bigger, that are bigger than a few hundreds of nanometers are a bit challenging to measure with the AUC because they sediment very quickly. But it's not a challenge that cannot be solved. You would have to do is increase the viscosity of your solution so that it allows you to the particles to sediment slowly, even at a high gravitational field. So AUC is actually, the smaller the particle, the easier the method is. But I think for particles that range from 1 to 20 nanometers, it's quite ideal. Above that size, it's still very good, very easy. But I think you would have to consider increasing the viscosity of your solvent in order to get enough data points for your measurement. But in general, it works for particles of all sizes. It all depends on how long the particles take to sediment inside the centrifuge. Yeah.
Very
yes.
good. At this time, I would just like to again thank Dr. Osman Bakr for providing a very informative talk on how good AUC can characterize particles, and I would also like to thank everybody in attendance of this webinar series. At this time, we will log off, and we appreciate your attendance. Thank you.
Thank you very much.